A very good morning to all of you all. This is Dr. Meena Shankarnarayanan, Professor and Head of Department of Mathematics, Anand Institute of Higher Technology, Karipattur, Chennai. I am here to give you a talk on the bridge course for mathematics. The need for bridge course. To bridge the gap between what students need to know before they step into learning advanced courses at the college level and what they are actually aware of from the intermediate level. Mathematics, the queen of sciences, the backbone of engineering, needs to be learnt with clarity. To cope up with the courses in the college level, it requires a good understanding of the concepts of different topics in mathematics. So, let's get started. The topics to be covered under the upcoming sessions are set theory, matrices, differential and integral calculus, differential equations, complex numbers, vector algebra, trigonometry, probability and statistics. Start our session with set theory, the most fundamental branch of mathematics. Let's see who are the brains behind this field. The contributors of set theory are Cantor, George Ferdinand Ludwig Philipp Cantor. He was a German mathematician who found set theory. Another contributor is John Venn. He was an English mathematician, a logician and a philosopher noted for introducing Venn diagram. Whatever we learn as a running text, we would often like to visualize things, and this mode of visualization was given by John Venn in set theory. Venn diagrams are not only used in set theory, they are used in probability, logic, statistics, computer related subjects too. Let's begin with what is a set. A set is a collection of well-defined objects. So what do we mean by the word well-defined? Let's be more clear about it. A set is well-defined if there is no ambiguity as to whether or not an object belongs to it. We have a few examples which is going to explain this concept a bit more clearly. A is equal to set containing red, blue, yellow, green, purple. We call this well defined because we know all the entries within the braces denote colors. Take up the next example which gives you the details of the days of the week. Again it's well defined. The last one, socks, shoes, pant, shirt, belt. They are all related in some form to a person wearing a dress. A shoes, a socks, a pant, a shirt and a belt. So once you know that they are totally related, you can call it as a set. Now let's make an attempt to see if we have understood the basic definition. Check if the following are sets. The first one, collection of the currently enrolled students at Anand Institute of Higher Technology with a grade point average above 7.0. Give it a try. This is a set because we know it is well defined. Why? Students at Anand Institute of Higher Technology with a grade point above 7.0. So the definition is clear over here, and we know we are considering students, hence it is called a set. Take up the next example, the collection of young faculty members who reside in Kelambakam. Here, faculty members, young faculty members. How young is young we don't know. Someone may say 15 is young, someone might say 25 is young, someone might say 30 is young, someone might say even 50 is young. So we don't know how young is young, so it is not well defined. Hence, the collection of young faculty members who reside in Kelambakam is not a set. Moving on to different ways to describe sets. Our textbooks will talk about the roster form and the set builder notation form. The very first notation is the verbal description of the elements of a set. So in general we have got three ways to describe the sets: name by name, or by roster form, or by set builder notation. By roster form is you list by listing the elements separated by commas and using braces to enclose the list. By set builder notation, that uses a variable and a rule to describe the elements of a set. So let's take some examples. Let us represent the collection of cities whose names begin with alphabet C in Tamil Nadu. This is the verbal form. Putting it down in the roster form, we are listing down the cities which start with alphabet C in Tamil Nadu. So we have Chennai, Coimbatore, Kadalur. In case I have missed out on something starting with C, kindly include it. Getting into the set builder form, which is the most important form for a mathematician to represent a set, is X. We read this as set of all X such that X is a city whose name begins with C in Tamil Nadu. Another example which you can see over here is the counting numbers, multiples of 7 that are less than 35, the verbal form. So numbers which are multiples of 7 and less than 35 in roster form is listed out: 7, 14, 21, 28. Don't include 35 because it's less than 35. The third one, the set builder form, is given by set of all X such that X is a counting number multiple of 7 that is less than 35. A task for you: describe the sets in roster form. A, set of first 5 natural numbers. I hope you all know what natural numbers are: numbers which start from 1. B, set of all whole numbers less than 8. Whole numbers are numbers starting from, complete it. C, X, set of all X is divisible by 12. Making mistakes is the right way to learn, so continue learning. Describe the sets in set builder form: 2, 4, 6, 8. So when I talk about set builder form, recollect the definition and then write it precisely as to how a mathematician might need it. So set of all X such that, complete it. Do not read mathematics, we need to work out mathematics. Element of a set. A member of a set is an object or idea in a set. Notation: X in S, or X belongs to S. So given an example, A equal to 1, 2, 3, we know 1, 2 and 3, they belong to the set. But take any other number which does not belong to the set. So does not belong, you have the notation given over here with a stroke on E. Different types of sets. The broad classification consists of finite sets and infinite sets. A finite set is a set which has finite number of elements. You can count the number of elements. While an infinite set is a collection of elements which cannot be counted. The set contains several elements and there is no end to it. So the empty set. The empty set, also called null set, is a set that has no members. This is an example of a finite set. So let me go through this example using the present situation, the lockdown period due to COVID-19. Phi is equal to the collection of people visiting a mall during COVID-19 lockdown period. Phi in roster form and phi in set builder form, which is given by set of all X such that X is a person visiting a mall during COVID-19 lockdown period. This is definitely not possible because a mall is not opened yet. An infinite set, example for it is C is equal to set of all X such that X is divisible by 12. So list out all multiples of 12. 12, 24, 36, etc. The list goes on. Hence it's called an infinite set. Beware, understand the concept clearly. Phi within braces does not symbolize the empty set. It represents a set that contains an empty set as an element and hence has a cardinality of 1. I am sure you should have learnt in school what cardinality is all about. It is nothing but the number of elements present in the set. Now moving on to equal sets. Two sets are said to be equal if they have exactly the same elements. An example out here is ACT, it's equal to CAT, TAC. We are not bothered, we are not particular about the order of elements in the roster form. It does not matter. Only thing you need to remember over here is do not repeat the elements inside the set bracket. Fine. So here from the second example where you have book, you have two O's, don't repeat it twice. It's not required at all. Subsets. A set A is a subset of a set B, or a set A is contained in set B. If you have that criteria, then we say A is a subset of B. So take an example. 1, 5, 7, 11 is A, and B has 3, 5, 11, 16, 1, 7, 9. So we have all the elements of A contained in B, and there are extra elements in B which are not in A. Thus we say set A is a proper subset of set B. In case all the elements of A are all the elements of B, then we'll say they are equal sets. Then we will also say it is not a proper subset because both are the same. A set is a subset of itself since a set contains all its elements. A is a subset of A. And similarly, the empty set is a subset of every set because every element in the empty set belongs to any set. Hope this is clear. Because every element in the empty set belongs to any set, since empty set has no elements. Power set. Think of it as all the different ways we can select the items. The order doesn't matter. Includes selecting none as well as all elements. A power set of S is a set of all subsets of S and is denoted by P of S. So taking up an example where set A comprises of elements A, B, C, put them down individually, pair two at a time, and then give the complete set. Do not forget your empty set. You should have studied this in your school, as number of elements contained in a power set is 2 power n, where n stands for the number of elements. A Venn diagram is a pictorial representation of relationship between sets. One would always have a better understanding of a topic if it can be visualized. So, a big thanks to Professor John Venn for his contribution to set theory. Venn diagram is also given other names like primary diagram, set diagram, logical diagram, logic diagram. This is because of its applications in various other fields. Here is a Venn diagram of A subset of B. A is contained in B and B and A are contained in the universal set U. The diagram shows that every element in set A is also in set B. Hope you have got a clear understanding of what a Venn diagram is now. Now we'll move on to set operations. Set operations contains mainly two operations, which are the union and the intersection. So let's look into what union of two sets mean. The set operation union brings together all the elements of both sets, whether those elements are in one or both of the sets. In set builder form, A union B is set of all x belonging to U such that x belongs to A or x belongs to B. There's a reason why OR has been highlighted. The Venn diagram for A union B is given with a simple example. A set of all A, B, C, D, B set of all elements containing B, D, E. A union B, pick up all the elements, don't repeat the elements, and now the diagrammatic representation, which is nothing but the Venn diagram. Make a note, A is a subset of A union B and B is a subset of A union B2. Intersection. The set operation intersection takes only the elements that are in both sets in set builder form. A intersection B, set of all x in U such that x is in A and x is in B. So the elements which are common to A and B from the previous example are B and D, and this is how you denote it in the Venn diagram. Make a note, A intersection B is a subset of A and B. Complement of a set. The complement of a set denoted by A dash is the set of all elements in the given universal set that are not in A. A dash, set of all x in U such that x does not belong to U. The example clearly illustrates what the complement of set A is. Do not learn the definitions as definitions. Try to give your own examples and try to figure out the concept behind the definition. So a small task. What is U dash? Given U stands for the universe, and what is complement of an empty set? These questions may sound simple, but just check if you are able to answer it. If not, U dash is nothing but elements which are not in U by definition. But what is U? U is the entire universe. Therefore, there can be no elements which are not in U. Hence, U dash is nothing but the empty set. Other way around, what is the complement of an empty set? What is not there in an empty set is all what is in the universe. Hope you enjoyed this task. Properties of union and intersection. Commutative property, A union B is equal to B union A. It holds good even for intersection. Associative property, A union B union C is equal to A union B union C, and A intersection B intersection C is equal to A intersection B intersection C. A union empty set is same as the set A. Similarly, when you take an intersection with an empty set, it is always the empty set. The distributive property, A union of B intersection C is equal to A union B intersection A union C, and A intersection of B union C is equal to A intersection B union A intersection C. This is followed by the De Morgan's law, the famous law, which is applied for any two finite sets A and B. A union B complement is equal to A complement intersection B complement, which is De Morgan's law of union. The same holds for intersection. A intersection B the whole complement is equal to A complement union B complement. You may have been asked to prove these laws given a set in school, but as you go into the higher stage of learning, you'll be applying these problems in some of the statement problems, like which you often see during your engineering course, as well in your final year, or when you take up your CAT exams or GRE or GATE exams. So understanding the concept at this level is definitely going to help you and make this journey smooth. Illustration using Venn diagram. You can do it for the other one. Now let's look into the terminology for logic and sets. How does the word OR differ in the following two scenarios? I told you when we spoke about the union that OR has been highlighted. So I am here to explain to you what this OR means in English and what this OR means in mathematics. Is there a difference? Let's look into it with an example. For idlis, I may have sambar or chutney. What are the options I have for idlis? So I can have sambar alone, I can have chutney alone, or I can have sambar and chutney. It's not going to matter. because sambar and chutney is readily prepared for me and I have been asked to take what I want from the options. The second example, I am trying to decide whether to stay back at home or go out on a Sunday morning. What options do I have for the morning? Look into this statement clearly. If I am going to go out, choose the option of going out on Sunday morning, I cannot be at home. Or if I am going to be at home on Sunday morning, I would not be out. So the or over here is different from the or which we see over in the first definition. It's a very beautiful example. So two different interpretations for word or may cause confusion in finding solutions to problems in mathematics. To overcome this problem, mathematicians interpret the word or as an inclusive or. So understanding or in mathematics with an example, x such that x is a set of factor of 12 or x is a factor of 10. Put down the factors of 12, put down the factors of 10. Now, when I am going to pick up the union, it's going to be, I am going to collect all the elements which are present in A or B and in A as well as B. So I have 1, 2, 3, 4, 6, 12 and the others 5 and 10. The phrase A or B means we have only A or only B or both A and B. The word or corresponds to the set operation union. Understanding and in mathematics. We are going to consider the same example as we had taken for or. So x, set of all x, x is a factor of 12. Set of all x, x is a factor of 10. So the common elements which belong to both of these sets are 1 and 2. The phrase A and B means both A and B. The word and corresponds to the set operation intersection. With this, we have come to the end of the module. Every module, once completed, will have a problem solving session. Give it a try. Once again, I repeat, making mistakes is the right way to learn. So we are here with the first question. In a class of 40 students, 12 enrolled for both English and German, 22 enrolled for German. If the students of the class enroll for at least one of the two subjects, then how many students enroll for only English and not German? Being the first question, I'll give you a clue. You're going to apply the formula n of A union B is equal to n of A plus n of B minus n of A intersection B. N stands for the cardinality of each set, the number of elements in each set, and A union B is nothing but, in this particular example, it's a set of students who have enrolled for at least one of the two subjects. A intersection B is the set of the students who have enrolled for both. Make an attempt. The next question follows in the same manner. You can also try drawing the Venn diagram and then come up with the correct solution. To have a better understanding of the subject, we need to take up slightly difficult problems, and this is one such problem. Another one for you. Some of the references include a few websites and some standard textbooks. A special thanks to Dr. Timothy Peel from the University of Minnesota. I think the problems given here will suffice for you to feel confident that you have understood this module. Hope you enjoyed the session. Let me again tell you, there is no end to learning. In case you have any clarifications, reach me on my mail ID meenayas.max@aiht.ac.in. Feel free to contact me on my mobile 9840 390 510. I am here to help you out. Thank you.